This material looks identical to styrofoam. Same color, same texture, same protective cushion around whatever fragile device is inside the box. But here's the part that should stop you in your tracks. It wasn't manufactured in a petrochemical factory. It grew itself, from mushroom roots, in just 7 days. And by the end of this video, you're going to see how this same underground organism is being used to replace plastic packaging, create luxury leather handbags, build boats that float in the ocean, and could one day help construct the first human habitats on Mars. This isn't science fiction, it's mycelium, and it might completely change how we make almost everything. Before we talk about replacing plastic or building houses, we need to understand what we're actually dealing with. When you think of a mushroom, you probably picture the cap and stem popping out of the soil after rain. But that mushroom, that's just the fruit. It's like an apple on a tree. The real organism is hidden underground. If a mushroom is an apple, mycelium is the entire apple tree roots, trunk, branches, everything. The visible mushroom is just the reproductive structure. The rest of the organism is a vast, invisible network beneath your feet. Mycelium is a web of microscopic threads called hyphae. And when I say microscopic, I mean hair-thin filaments that branch, fuse, and expand in every direction. Under a microscope, it looks like a living internet, a dense, interconnected network constantly growing, constantly searching. But here's where it gets mind-blowing. Mycelium doesn't just sit there. It eats. Not in the way animals eat, but in a far more efficient way. It secretes enzymes into its environment, breaking down organic matter like wood chips, agricultural waste, and plant fibers into digestible nutrients. Imagine pouring a dissolving liquid over a pile of wood and watching it slowly transform into food. That's what mycelium does naturally. And as it digests this material, those microscopic threads grow around it, weaving through it, binding it together like nature's own glue. That binding ability is the secret. Because when mycelium grows through a loose pile of agricultural waste, it doesn't just consume it. It turns it into a solid, lightweight composite material. In other words, it grows structure. And if you think that's impressive, listen to this. The largest living organism on Earth isn't a whale. It's not a giant redwood tree. It's a honey fungus mycelium network in Oregon that spans 2,385 acres, nearly 4 square miles. One organism, hidden underground, estimated to be thousands of years old. For over 1 billion years, about 1.3 billion, according to fossil evidence, fungi have been perfecting this technology, growing, binding, digesting, regenerating, and humans are only now beginning to understand how to work with it. Because once you realize mycelium can grow into shapes, once you realize it can bind waste into solid forms, you start asking a dangerous question. What if we stopped manufacturing materials and started growing them instead? And that question leads directly to packaging. Plastic packaging is everywhere. Open a new laptop, buy a TV, order something fragile online. Chances are it's protected by expanded polystyrene styrofoam. It's cheap, it's lightweight, it absorbs shock, and it takes more than 500 years to decompose. 5 centuries. That packaging you throw away today could still exist in the year 2526. Now compare that to this. Mycelium packaging decomposes in about 45 days in your backyard compost, not in a specialized industrial facility. Your backyard. That difference alone would be revolutionary. In 2007, in Troy, New York, a company called Ecovative Design was founded with a radical idea: grow packaging instead of manufacturing it. They developed what they call mycelium foundry technology. Here's how it works. Step 1: agricultural waste. Things like corn stalks, hemp herds, rice hulls, materials farmers often struggle to dispose of. Step 2: mycelium spores are added. Step 3: that mixture is packed into a mold shaped like the protective packaging you want. Then you wait. Over the next 7 days, the mycelium grows. It spreads through the waste, digesting and binding it. Thread by thread, it stitches the particles together into a solid form that exactly matches the mold. No melting plastic, no high-pressure petrochemical processes, just growth. Once it fully colonizes the mold, heat is applied to stop the growth, essentially deactivating the organism. What you're left with is a rigid, lightweight structure. Major brands like IKEA and Dell began adopting mycelium-based packaging for certain products. Because it works. It absorbs shock. It insulates. It's flame-resistant. And when you're done with it, you can literally crumble it into your garden. Every year, the world produces more than 400 million tons of plastic. A significant portion of that is single-use packaging. Now imagine even a fraction of that replaced by materials grown from agricultural waste. Waste turned into protection. Protection turned back into soil. That's not just sustainability. That's a closed loop. But packaging is just the beginning. Because once companies realized mycelium could be molded into rigid shapes, someone asked, what if we could grow something flexible? Something soft? Something that feels like luxury? Leather is complicated. It's durable, breathable, timeless, and it comes from animal hides with all the environmental costs that entails: land use, water consumption, methane emissions, chemical tanning. Most vegan leather you see today is plastic. Polyurethane or PVC-based materials designed to mimic leather texture. They look good, but they're fossil fuel products, which is why companies like MycoWorks took a different path. Instead of synthesizing leather, they decided to grow it. MycoWorks developed what they call fine mycelium technology. Rather than letting mycelium grow randomly, they control its growth conditions, temperature, humidity, nutrients, guiding the cells to self-assemble into dense, interlocking networks. Think of it like training vines to grow along a trellis in a specific pattern. The result is a material with a fibrous structure remarkably similar to animal leather's collagen matrix. Strong, flexible, breathable, and because it's grown, not extruded from plastic, it behaves more like natural leather. In 2021, luxury brand Hermès partnered with MycoWorks to create the Sylvania bag made from mushroom-based material. One of the most prestigious fashion houses in the world chose mushroom roots over synthetic plastic alternatives. Not as a gimmick, but as a premium material. Because fine mycelium can be embossed, dyed, stitched, and finished just like traditional leather. It ages gracefully. It feels real because structurally it is real. It's a natural fiber network. Another company, Bolt Threads, developed a similar material called Milo. Their process also grows mycelium sheets, then stabilizes and finishes them for fashion use. Traditional leather production can take years, from raising livestock to processing hides. Mycelium leather can be produced in weeks. From lab to sheet. You're compressing years of biological growth into controlled indoor cultivation cycles. And because it's grown in vertical farms, it doesn't require grazing land. No deforestation, no methane emissions from cattle, just controlled growth in a facility. Now imagine the implications. Shoes, car interiors, furniture upholstery, luxury goods that don't rely on animal agriculture or fossil plastics. But if mycelium can create rigid packaging and flexible leather, could it do something even bigger, like replace parts of our buildings? Concrete and steel built the modern world. They're strong, they're reliable, they're carbon intensive. Cement production alone accounts for roughly 8% of global carbon dioxide emissions. Now imagine if some building components could be grown instead of fired in kilns at 1,400 degrees Celsius. Researchers at Penn State University, EMPA in Switzerland, and Eastern Connecticut State University have been studying mycelium-based composites for construction. They grow mycelium through substrates like hemp or sawdust in brick-shaped molds. Once heat-treated, the blocks become lightweight, rigid, and surprisingly strong. They're naturally fire-resistant. They offer excellent thermal insulation, and they're far lighter than traditional masonry. Traditional fiberglass insulation has an R value in a similar range to certain mycelium composites, but fiberglass requires high-temperature manufacturing. Mycelium grows at room temperature. That's a radical shift in energy input. And then there's this story. A 1-4-foot boat, built by Byers Gamber using wild polypore mycelium grown on hemp substrate. It weighs just 72 pounds. And it floats, a seaworthy vessel, grown from fungus. Researchers are even exploring self-healing concrete using fungi embedding spores within concrete that activate when cracks form, producing minerals that seal the gaps. Buildings that repair themselves. Acoustic panels made from mycelium composites are already being used for sound absorption, lightweight, biodegradable alternatives to synthetic foam. So now we've replaced packaging. We're challenging leather. We're entering construction. But what happens when you take this idea off Earth? Sending building materials to Mars is brutally expensive. Every kilogram launched into space costs thousands of dollars. So what if, instead of shipping tons of steel and concrete, you ship spores? NASA has been researching the concept of mycelium-based habitats for Mars. The idea is elegant. You send a lightweight structure containing dormant fungal spores. Once astronauts arrive, they add water and feedstock potentially derived from Martian soil combined with biological waste. The mycelium grows, expanding and reinforcing the structure from within. You're not transporting heavy building materials. You're transporting instructions for growth. Biology as manufacturing. Habitats that could potentially self-repair. Structures grown on-site using minimal imported mass. If fungi have survived mass extinctions, radiation, and extreme environments on Earth for over 1 billion years, they might be some of the most space-ready organisms we know. Researchers are exploring mycelium-based electronic substrates, biodegradable circuit boards, packaging that can be programmed to decompose on a schedule, materials that grow into complex shapes without machining. We're talking about a future where supply chains look less like factories and more like farms, where waste becomes feedstock, where growth replaces extraction. We started with a white block that looked like styrofoam. 7 days of growth, 45 days to disappear back into soil. From there, We moved to luxury handbags made from mushroom roots, to boats grown from fungus, to research labs exploring living habitats on Mars. What connects all of it is a simple but radical idea. Instead of forcing materials into shape with heat, pressure, and fossil fuels, we can guide living systems to grow the shapes we need. Fungi have been doing this for 1.3 billion years. We're just now learning how to collaborate. And maybe the most exciting part? We're still at the beginning. The next decade could redefine what you think materials are. Which application surprised you most? Packaging, leather, construction, or Mars habitats? Let me know. And if you're fascinated by the hidden biology reshaping our world, make sure you subscribe. Because we're only scratching the surface of what fungi can do. Until then, look a little closer at the ground beneath your feet. There's an entire manufacturing network down there, growing,